Charan, charan. Medyo matagal yung recording. Okay, there we go. We're recording. Good morning, everybody, and welcome back to Math 174, or welcome back to ACAD mode again. Medyo ano no, medyo nakakawala ng momentum yung reading break, especially that in the supposed break there was a typhoon that we need to contend with. So I hope you guys are you were safe and hindi masyadong naapektuhan ng bagyo. Kung naapektuhan din kayo katulad ko, hopefully nakaka-recover na kayo ano. But yeah, medyo anticlimactic nga yung reading break. I guess there's a dilemma for the reading break that before the reading break we're building up the momentum. Ano, ang hirap mag-adjust pabalik sa academic shape after the semestral break ano. Tapos nung medyo nasa mood na tayo, we have our momentum going on, bigla tayo mag-reading break. Tapos ngayon medyo minalas pa tayo kasi aside from the reading break, we had a typhoon to contend with. But I hope you find a silver lining to this long break. You were able to catch up with your ACADS, you know. But it's a double-edged sword for us because nabawasan ng 2 linggo, or actually nabawasan ng 1 linggo yung ating schedule. And medyo ang bagal ko na magturo, nabawasan pa tayo ng 1 linggo. So that's why I decided to skip module number 5. So if you see, I gave you access to module number 5, but today I'll be doing module number 6. But don't worry, I won't give any assessment for module number 5. It's just an optional reading for you. And actually, it's a good, it would be a good topic for your project later on if you decide to do curve fitting. I know because module number 5 tackles one of the shortcomings of interpolation. And as some of you have written in problem set 1.1, ano, sabi nila isang problema sa interpolation ay, or isa sa mga realizations nila from the class is that medyo limited yung interpolation. Sa simula, akala nila pwede nilang gamitin sa forecasting yung interpolation. Kasi ang ganda nga naman, ano, meron kang discrete set of data, then we're able to connect the dots through a curve and then get a function that will pass through all of these data points. And it's quite natural to think, oh, maybe I can use it to do prediction or forecasting. Ano? Pero our dreams were shattered when we look at the theoretical error. When we look at the theorem, that theorem, I think it's theorem 2.4 or 2.3, we learned na nakokontrol lang pala natin yung error, or we only have an idea of how much the error is in the interpolation process within the interpolatory interval. And that's why it's called interpolation, inter. So ibig sabihin, nandun ka lang sa loob ng interpolatory interval. So you can use the interpolatory function that you created to estimate function values within the interpolatory interval. But outside of the interpolatory interval, who knows what will happen? Ano, posibleng mag-blow up yung error, kaya hindi nyo posibleng gamitin or hindi pwedeng gamitin yung interpolation to forecast because we don't have any idea of how big the error can become outside of the interpolatory interval. And I think you have seen this in some of the laboratory exercises nung medyo pinalaki natin yung graph, ano, in-extend natin yung graph ng isang function at saka ng kanyang interpolatory function. Ang ganda ng match within the interpolatory interval, but the moment you get out of that interpolatory interval, things go crazy. Ano? Medyo lumalaki na yung error. So, as to address that problem, ano, kung ang gusto mo talaga ay mag-forecast, ang kailangan mo gawin ay mag-curve fitting. All right? And that's what module number 5 starts to talk about. Some basic curve fitting techniques na given ka ng set of data points, hahanap ka ng isang approximating function. Take note of the change of word. Approximating function kasi ngayon, hindi natin papadaanin yung, or hindi natin i-require yung approximating function to pass through all of the data points. What we want to do is to mimic the behavior of the function that will allow us to use our function to forecast values or function values outside the interpolatory interval. So meron tayo dong linear regression, quadratic fit, power fit, and so on. So kung ganun yung gusto nyo, halimbawa, you're interested in monitoring stocks, ano, pwede kayong pumunta sa chapter 5, sa module 5, tapos tingnan nyo ano yung mga methods na pwedeng gamitin para mag-curve fit ng, or mag-curve fit para sa stocks. para ma-forecast nyo, say, after 30 days or after 60 days, magkano na yung presyo ng isang stock na minomonitor nyo, no? Nung nag-175, medyo medyo amazing para sa akin yung etong mga techniques na to because I really love monitoring these statistics, mapa-basketball yan, mapa-finance yan, I keep sometimes if I'm really invested in one thing, gusto ko mag-invest San Miguel Corporation and I want to buy some stocks. So I get the data, download ko lang sa kung saang website, tatali ko yung presyo for 1 month and then I'll buy a stock and then magpo-forecast ako ngayon magkano yung makukuha kong profit after 30 days. At kapag halimbawa na-achieve ko na siya earlier, then I will sell my stocks to realize some profits. So hopefully you get those realizations na talagang ang daming pwedeng paggamitan ng topics natin sa 174. All right? But again, that's one thing. It's a shame that I need to skip module number 5, but it would be necessary. Okay? Kasi sa course outline, yung chapter 1 talaga, interpolation lang. It's just an added module na nilagay ko just to address yung problema ng interpolation na hindi natin siya pwedeng gamitin pang forecast. Now we'll be moving forward to the second chapter of the course, which will be shorter than the first one, and this is numerical differentiation. Now we start with module number 6. And here are our objectives for this module. So at the end of the module, and this is what I expect you to do in the next laboratory exercise, you should be able to derive a finite difference formula for numerical differentiation of a certain order. I will tell you, say, use 4 points to get a differentiation formula of order 5 or order 2. So dapat magawa niyo yun in the laboratory exercise. So you see here, you will not just be fed with the formulas, right? Tinuturuan namin kayo kung paano mag-derive ng formulas. So it's not really just a programming course wherein you get the formula from the book and then you try to write it into a computer program. That is the domain of computer scientists or computer programmers. As mathematicians, our goal is to understand these processes and design our own processes based on our understanding of prior methods. Kaya kung makikita nyo, ang design ng course ay ganito. May isang real-life problem, Tapos hindi siya na-address ng traditional calculus or ng classical calculus. Halimbawa, meron kang data points, gusto mong i-optimize, pero hindi mo ma-apply yung first at saka second derivative tests kasi wala kang continuous function. So una natin yung ginawa. And then parang okay na yung buhay natin. Meron na tayong function na pwede nating i-differentiate or function na pwede nating i-integrate depende sa application. Kaya lang ang problema, titingnan natin, gano'n kaya kalaki yung error? And is there a way on how we can improve this, say by choosing the abscissas wisely or by increasing the number of points used? So ganun yung gusto kong makuha yung takeaway rito. Get the classical techniques, then try to see what are their advantages, their disadvantages, and see how it is addressed and how the methods were adjusted to or improve to get better performance. So yun yung una. So sana matutunan nyo paano mag-derive ng finite difference formula. And yes, Kiefer, I'm sharing my screen. So if you're not able to see it, let me restart it. Okay. So yun. And then the second goal. Hold on. Wala kasi yung ibang copy nung slide. So yung nasa screen lang din. Anyway, so the second is to determine an upper bound for the numerical for the error incurred in numerical differentiation. Typo here. And probably it's been here for a year now. Hindi ko pa rin correct. So yeah. Hopefully you can see my screen now. So number 2, titingnan natin gaano kalaki yung posibleng maging error or what's the worst case scenario? What's the biggest possible error for our numerical differentiation formula that you derived in number 1? So laging ganoon, pag nagde-derive kayo ng formula, hindi sufficient na sabihin nyo, okay, ito yung gamitin mong formula. For us, mathematicians or numerical analysts, kailangan magbigay tayo ng idea. Ito yung ipang-approximate mo, pero ganito yung kalaki yung posibleng maging error. Alright? So laging magkakakibat yan. Numerical method plus an estimate for the error. So you should also learn how to do that or how to find an upper bound. And of course, our mainstay objective is for you to be able to use numerical differentiation to solve scientific problems. Okay? Now, let's get going kasi naubos ko na yung 11 minutes kakadaldal, ano? Kaya naubos yung oras natin eh. But anyway, so just a practical scenario, ano? As like in interpolation, ano? Parang ang dami na nating natutunan mula sa calculus, pero makikita natin na hindi pala siya laging applicable right away. Because if I give you a function, even a crazy function, tas sinabi ko sa inyo na kunin niyo yung derivative niya, you can do so if you're patient enough, right? You just need to recall basic derivative formulas for the functions plus differentiation rules, addition, multiplication, or the quotient rule, and then ano pa ba? Quotient, power rule, chain rule, implicit differentiation, and so on. So in summary, and I guess in the whole of calculus, pinakamadaling gawin talaga ay differentiation. Kasi kailangan nyo lang i-follow yung formulas or the rules of the game, right? So I hope you see calculus that way. Parang isa lang siyang laro na maraming rules na kailangan yung i-apply in the right order or in the right instances, ano. So kapag meron kang function, however complicated it is, as long as you have your differentiation formulas with you and you remember the basic differentiation rules, then just with the pinch of patience, you will be able to find the derivative, right? Pero ang problema, katulad nung nakita natin sa interpolation, yung nakukuha naman nating data sa totoong buhay ay hindi function kagad. It could be a discrete set of data, measurement data you take from experiments. Halimbawa, if you want to compute the coefficient of friction. Ang coefficient of friction denoted by the Greek letter, anong Greek letter to? Mu. So if you have the Greek letter mu for your coefficient of friction, it is basically the derivative of F all over F, where F is the force needed to overcome a certain um, force in an object. So in particular, si F ay yung force required to overcome a 5-pound restraining force with respect to an angle theta. The angle theta is the angle made by the pole. Okay? So meron ka kasi ditong pole, tas meron kang rope na naka-wrap doon sa pole. And if the angle between those two between the flexible rope and the post is theta, then the coefficient of friction, which is a constant, it is just the ratio of the first derivative of F all over F, right? So this is the formula for the coefficient of friction, and it is a constant of proportionality. So that means whatever your theta is, dapat constant, yung F prime over F. Now, if you want to calculate the coefficient of friction for this particular setup, so meron kang pole, gusto mo makita ano yung coefficient of friction dun sa pole and the flexible rope that you have, then you need to compute this guy. But of course, it's hard to do that, right? So what you can do is to get measurements, experimental measurements. So halimbawa, pwede mong gawin, i-force mo halimbawa or you get the force required to overcome the 5-pound restraining force doon sa iyong setup at varying angles theta. So halimbawa, ang ginawa ko, so halimbawa 0 degrees yung angle sa kanila, kailangan ko ng 5 newtons of force or 5 newtons of force to overcome it. When the angle between the rope and the pole is pi over 2, I needed 7.83 newtons, and so on. So you get this table of values, and since you want to get the derivative, hindi natin gusto nating mahanap yung derivative para ma-compute natin si mu, which is f prime of theta all over f, but we need f prime. And actually, kailangan ko rin si f. And I don't have those functions because what I have instead is a discrete set of experimental data. All right? Now, natutunan na natin mula sa chapter 1 how to find a function that will pass through all of these data points. So getting capital F is not a big problem for us. right? You can just apply your usual Lagrange interpolating polynomial formula to get a certain polynomial uh, that will pass through all of these data points. Ilan bang data points natin? 1, 2, 3, 4, 5, 6. We have 11 data points, right? Tama ba ang bilang ko? Yeah. 11 data points, so we'll get a polynomial of at most degree 10. Okay? Now, nirun ko lang yung aking Lagrange interpolating polynomial program, and I get this as my approximate for capital F, right? So okay na tayo dun sa denominator. We have a function, capital P, that approximates or that interpolates capital F, all right? So tapos, kailangan ko si f prime para makuha yung numerator para dun sa coefficient of friction. So, dahil meron lang akong discrete set of data, I cannot find f prime right away. Okay? And, well, naturally, our question is, how can I get f if I do have capital P na? All right. So naturally, the thing to do is to get the derivative of your interpolating polynomial. And if we know that we have a good approximation for capital F, we can use that good approximation to capital F to get a good approximation for F prime, right? So ibig sabihin kung si capital F ay in-approximate ko by capital P, then the derivative of P, common sense tells us, or intuition tells us, that P prime should be close to F prime, right? And that's what I did here. Kinuha ko lang yung derivative ng ating interpolating polynomial, right? And this will give you one way of finding numerical differentiation formulas. Kung given ka ng discrete set of data points, all right? Pwede mo palang ma-approximate yung numerical, yung derivative ng iyong function that will pass through your discrete set of data by simply differentiating the interpolating polynomial. Kunin mo yung interpolating polynomial, kunin mo yung derivative niya, and that's your estimate for the derivative, right? And that's that simple, all right? So, and with that, pwede ko na tapusin yung chapter 2 with that. Ano? So, kung given ka ng discrete set of data points, kunin mo lang yung Lagrange interpolating polynomial, kunin mo yung derivative ng Lagrange interpolating polynomial, then you're done. You have your numerical differentiation formula, right? And that's one way. And actually, in most cases, you will survive with only that knowledge. And that's how powerful interpolation is. Kaya sa design ko ng 174, kalahati talaga nung SEM nasa interpolation. Kasi you can extrapolate concepts and sasabihin mo, yung chapter 3 ay numerical integration. So malamang, pwede kong gawin pag given ako ng discrete set of data, kukunin ko lang yung interpolating polynomial para dun sa discrete set of data points na yon. Tapos yun ang i-integrate ko para makakuha ng numerical integration technique. And you will be right. Okay? So, ganun yung first strategies, right? But para hindi masayang yung natitirang mga panahon sa semestre, ano, titingnan natin ano yung alternative ways rather than simply finding the interpolating polynomial and differentiating it. Kasi one thing about interpolating polynomial ay medyo mahal yung proseso. If we will do it that route, so pag given ka, halimbawa, katulad dito, given ka ng 10 data points. So, ang gagawin mo muna, magla-Lagrange interpolating polynomial ka. Right? So, you will get a degree 10 interpolating polynomial for these 11 points. Tapos, i-differentiate mo siya. So, you eventually are doing two things. You're doing the interpolation, then you'll do the differentiation. And medyo mahal yung proseso na yun. Maybe there's a cheaper way to get a good estimate for the derivative. And that's what we will do in the next few sessions. Ano? So, yun. Meron tayong dalawang paraan ng numerical differentiation formula. Una, i-differentiate nyo lang yung interpolating polynomial. And I won't discuss too much about that because it's very simple. Run the Lagrange program that you have from chapter 1. Then, kunin mo yung derivative ng interpolating polynomial. Then you're done. You have your numerical differentiation technique. All right? Pero siguro may iba pang paraan on how to do it that we don't need to use many points, all right? And get some good measure, some good approximates also, okay? Yun yung titingnan natin sa mga susunod na sections dito sa Module 6 and probably Module 7, okay? So any questions so far? So pag nagpa-essay uli ako sa problem set 2, pwede kong tanungin, pwede kong itanong, discuss two ways to derive numerical differentiation formulas. Although we just spent 10 minutes talking about it, you should be able to write firstly, pwede mong gamitin yung interpolating polynomial. Just differentiate the interpolating polynomial and ergo, you're gonna have a numerical differentiation technique. All right? Tapos yung second ay yung paggamit ng finite differences, which is hinged on the use of Taylor's theorem, and that's what we'll do in the next few minutes. Okay? So questions so far? Oh, by the way, hindi ko pala pinakita yung resulta nitong itong experiment na to, So if you compute for mu, all right? Kukunin lang natin yung p prime over p, okay? Tapos, so meron tayong interpolating polynomial, kunin mo yung derivative niya, divided by the interpolating polynomial, and that's going to be our estimate for the coefficient of friction. Now, we know that the coefficient of friction should be a constant, so ipa-plot ko lang to for all theta values between 0 and 5 pi. Actually, you can just, 0 to 5 pi, tingnan ko lang siya. Ito yung makukuha kong graph para kay u theta, mu tilde of theta, right? And you will see that almost on the entire interval 0 to 5 pi, nag-stabilize yung mu tilde sa value na 0.286. Since I am expecting the coefficient of friction to be a constant, I will look at this graph and see saan nagko-converge yung mu tilde, right? And mu tilde seems to be stabilizing around the constant 0.286. So I can say, the coefficient of friction is approximately 0.286. Okay? And that's what we have here. Okay? Now, siguro tingnan natin. I've mentioned that just differentiating the Lagrange interpolating polynomial will give you a numerical differentiation formula. Well, you can also say something more or get something more from the Lagrange interpolating polynomial. You will not just be able to find an estimate for the derivative, right? But you can also find an estimate for the error. Okay? So paano niyo makukuha yung error bound para sa numerical differentiation formula you obtained by using the interpolating polynomial? Well, actually, it's just easy. Just include the error term in your differentiation process, and that will also be the error involved in the differentiation process. So for instance, and I hope you can extend this idea, no? So halimbawa, gusto kong i-estimate yung derivative using 2 points. Okay? So halimbawa, meron akong dalawang abscissas, si x sub 0 at saka si x sub 1. Gusto kong gamitin yung Lagrange interpolating polynomial to get an estimate for f prime of x sub 0. Right? So, yung natutunan nating method kanina, kunin lamang natin yung interpolating polynomial na daraan kay x sub 0, f of x sub 0, at saka x sub 1, f of x sub 1. If you do the Lagrange form, you will get this. Ito yung interpolating polynomial natin na daraan dun sa dalawang data points. All right? And this is fine because this is a linear function. We have 2 points. So that means we'll have a polynomial of degree at most 1. Tapos, if you want to get an idea, so kung gusto mo lang ay derivative formula, i-differentiate mo lang ito. But if you want to also know how accurate that numerical differentiation formula, so isama mo dun sa manipulation yung error term, right? Remember, this is the error term. This is the n+1 derivative of f evaluated at some number psi all over n1 plus n+1 factorial, where n is equal to 1. Kasi ang n plus 1 points natin ay 2. So ibig sabihin n is equal to 1. So you have second derivative of c all over 2 times omega. Omega is the product of x minus the abscissas. Alright? So ito yung error term. Isama niyo siya dun sa manipulation. So you want to get a differentiation formula for f prime of x sub 0. So ang gagawin ko, i-differentiate ko lang ito. Okay? Pag differentiate niyo yan with respect to x, you will get this guy. Alright? So ito, linear lang naman to, linear function. Ang derivative niya ay just the coefficient or the slope. So 1 over the constant times the constant plus ganun din yung nangyari rito. Tapos ito, i-differentiate mo. Ang f double prime of c is a constant, right? Because c is a constant between x sub 0 and x sub 1. Hindi nga lang natin alam yung value niya, pero sure tayo si c ay constant. So this guy is a constant. So dito lang tayo magkakaroon ng problema. Because here you need to apply the product rule because you are multiplying two functions of x. So kaya nagkaroon ka ng dalawang terms dito. Produkto yan ng product rule. All right? And then since we want a formula for f prime of x sub 0, at this particular point, I will plug in x equals x sub 0. And hence, we will get this formula. Ito yung estimate natin for f prime. And the nice thing about, para kay f prime of x sub 0, and the nice thing about this formula is we do have a nice way of how to compute the derivative, but not just that. All right? Hindi lang yun. Meron pa tayong estimate para dun sa error. Because if you want to compute the derivative, ito yung gagamitin mong estimate. Kasi ito yung derivative ng interpolating polynomial evaluated at x sub 0. This guy will be your error term in the differentiation process. Okay? So, ibig sabihin, yung error dito ay nakadepende pa rin dun sa second derivative of f evaluated at c all over 2, which is basically the same constant you see in the error for the interpolation. Tapos, hindi lang yun. Meron siyang factor, pero mas madali yung factor kanina. Yung error sa interpolation ay x minus x sub 0 times x minus x sub 1. Ngayon, ang factor na lang natin ay x sub 0 minus x sub 1. Right? So if I will ask you, look at equation 6.5. So if I will use this formula for my derivative or my estimate for the derivative, how can I make it accurate? Kung gusto ko ng accurate na estimate para sa f prime of x sub 0, taking into account formula 6.5, paano ko mapapaliit yung error? Kasi dito for sure, kailangan kong gamitin si x sub 0, right? Because that's the point of interest. Now, my freedom kayo to choose is what x1 will become. All right? Kasi si x sub 0 fixed siya. Gusto mong i-estimate yung f prime of x sub 0. So si x sub 0 ay fixed. So may freedom ka ngayon to choose x sub 1. So if you have such a freedom to choose x sub 1, how should you choose x sub 1 so that the error is minimized? Ano yung magandang gamitin to be your x sub 1? Sige nga. Habang sisip-sip muna ako ng kape. Medyo 30 minutes na akong nagmo-monologue dito. So, do you guys see the question? Meron akong x sub 0. Gusto kong i-approximate si f prime kay x sub 0. Ngayon, na-compute ko. Equation 6.5. Kailangan ko lang palang pumili ng isang x1. Para tapos yung function value kay x1 siya yung gagamitin ko rito. Alright? So, ang question is, how should I choose x sub 1 to get an accurate estimate for f prime of x sub 0? Sige. Look at 6.5. Or nag-adjust pa rin kayo sa pagbalik after the reading break? Come on, guys. How should x sub 1 be chosen so that we get a small error using equation 6.5? Wag na mahiya. Libre naman ang hula. Unless super delayed yung connection ko at hindi ko nakikita yung chats nyo. Elgin says, Chebyshev or Legendre polynomial, sabi rin ni Kian Keefe. Well, that could be, yeah, you can do that. Though medyo high level na yung naisip nyo. All right. So yeah, that could be a solution. All right. I'm just not sure how good that solution would be. Maybe if we'll follow interpolation theory, if you are more into minimizing the L infinity norm, then you go Chebyshev nodes. If you want to minimize the L2 norm of the error, then you go Legendre nodes. All right. But yeah, those are good ideas. Pero napaka high-tech na. Mas simple yung hinahanap kong sagot. Just look at equation 6.5. How do I make the error term smaller? Come on. Madali lang to. Yun yung problema minsan sa math, no? You are overthinking. Ano? Sabi ni Neo, dapat si x1 ay much, much, much greater than x sub 0. Well, actually, I don't want that, Neo. All right? But good try, though. Bakit ay, yeah, tingnan niyo yung formula, 6.5. Ano dapat yung relation ni x1 at ni x sub 0 para maliit yung error? Mas simple yung sagot kaysa sa Legendre at Chebyshev. Get the limit as x1 approaches x sub 0. Bawal mag-limit, Elgin. Kasi nga, gusto nating ipagawa to sa computers. Ang alam lang ng computers, basic arithmetical operations. Hindi sila marunong mag-limit. But now I realize what you might be saying, Elgin. Yeah. In simpler terms, gusto ko lamang piliin si x1 na maging malapit kay x sub 0. All right? Bakit gusto ko si x1 maging malapit sa x sub 0? Kasi kapag si x1 ay super lapit kay x sub 0, yung x0 minus x1 na nandito sa error term ay liliit. Right? When x1 is very close to x sub 0, this difference will be very small times whatever this constant is, liliit yung error term. Remember, this is my error term, and I was asking you, paano ko mapapalit yung error term? Ang sagot lang, piliin si x sub 0 na maging malapit kay x sub 1. Or the other way around. Piliin si x sub 1 to be malapit kay x sub 0. Because if those two numbers are close to each other, that means x sub 0 minus x sub 1 will be a very small number times this constant, which we don't have any control with. So, liliit itong error term kapag si x sub 0 ay malapit kay x sub 1. Right? So, that's one way to look at it. All right? Paliitin yung difference between x sub 0 and x sub 1. But there's another way to look at it. Look at the numerical differentiation formula. Here we're saying that f prime of x sub 0 is approximately equal to f of x1 minus f of x sub 0 all over x1 minus x sub 0. Ano nga tong quantity na to, if you remember? This should ring a bell. Ano nga to? Anong tawag dito sa quantity na to? Yes, Mitzi is right. Ito yung slope, right? This is the slope of the line passing through x sub 1 minus x sub 0. So siya yung slope ng secant line, right? The line passing through the 2 points, right? Kaya siya slope ng secant line. But what is the right-hand side? What is f prime of x sub 0 again? In terms of a geometric interpretation? Oh, thank you, JR, Trisha, and Kian for replying to the previous question. Now the question is, ano nga si f prime from a geometric point of view? F prime is the what? Yeah, I know that's the instantaneous rate of change, but geometrically speaking, f prime of x sub 0 is... Come on, guys. Ano interpretation kay f prime of x sub 0? Ay nako, susumbong ko kayo sa Math 36 teachers nyo. Buti hindi pa ako nagtuturo ng 36 since bumalik ako. Ano ang interpretation kay f prime geometrically? Ay nako, next time pag face-to-face tayo ng 175, magtatawag talaga ako. This is what? This is the slope of what? Do you guys remember? Yeah, Key and Keefe is correct. This is the slope of the tangent line, right? And what's the relation between the slope of the secant and the slope of the tangent line? The slope of the secant line is the limit of the slope of the tangent line. Sorry, the slope of the secant line. Sorry, the slope of the tangent line is the limit of the slope of the secant line. Meaning, lagyan mo lang to ng limit as x sub 1 approaches x sub 0, then the approximation becomes exact. At siguro ito yung sinasabi kanina ni Elgin. Kasi nga ito, pag kinuha mo yung limit nito as x sub 1 approaches x sub 0, you get the actual derivative. And that's another way of looking at how do we make 6.5 much accurate, right? But either way, we come up with the same conclusion that x sub 1 should be very, very close to x sub 0. Whether you're looking at it as slopes of secant and tangent lines, or you're more analytical and you just look at the error term or the formula or the formula for the error. Okay. So sana you can do this. You can do the same analysis if I say compute f double prime using 3 points, right? So try to think about it. Maybe in the second problem set, that could be a candidate for the theoretical or proving question number 2. All right. So pwede nyo siyang pag-isipan. Okay. But the main agenda for the unit is to do approximations by finite differences. But before we go here, any questions so far? Okay. So kung wala, so let's move on to this topic. And this is what I'm telling you kanina na pwede na nga nating tapusin yung chapter kasi we can just build on our notion or our knowledge of numerical of polynomial interpolation. Tapos let's call it a day. I-differentiate ko lang yung interpolating polynomial. I can also differentiate the error term to get an idea how big the error will become. So mukhang kompleto na yung theory. But again, it's a costly process. You need to interpolate first and then you differentiate. That's a two-pronged process. Now, maybe there's a cheaper way on how to develop numerical differentiation formulas, and one such way is via finite differences. And the cornerstone of approximation by finite differences is Taylor's theorem. So babalik tayo sa Math 38. So hopefully from Math 38, you know that if your function is infinitely smooth, so ibig sabihin si f at ang lahat ng kanyang derivatives of any order ay continuous, then f of x plus h can be written as this infinite series. It is the summation of h to the power n times the nth derivative of f evaluated at x all over n factorial, and you take the sum from 0 to positive infinity. All right? So ito yung Taylor series expansion, where h is, let's assume h to be a positive constant. So si h ay positive constant. So if h is small, then most likely this sum will converge, and this sum will converge to f of x plus h. Or in explicit form, f of x plus h is f of x plus h times f prime of x plus h squared f double prime of x over 2 factorial and so on. So ngayon pa lang, I hope you start memorizing this or know this by heart kasi ang dami niyong paggagamitan in your mathematical career. Madalas niyo makikita yung Taylor series expansion. So if you didn't see its value in Math 38, ngayon makikita nyo saan ginagamit yung Taylor series expansion. And it's very powerful because kahit gaano ka-komplikado si f, yung value ni f of x plus h can be written as a series expansion, right? Actually, hindi lang function evaluation yung purpose ng Taylor series expansion, magagamit din natin siya sa pagkuha ng numerical differentiation formulas. All right? So just remember equation 6.6, right? And the nice thing about the Taylor series expansion, if the expansion converges, then you can just cut it off or truncate it to a finite number of terms. Sa halimbawa, gusto ko lamang hanggang degree n expansion. So kunin nyo lang yung first n plus 1 term. So that means you get the 0th term until the nth term, right? Ito yung tinatawag nating Taylor polynomial of degree n. It's degree n in the variable h. All right? So yung may h to the power n, siya yung last term. Pag yun yung ginamit yung last term, you get the polynomial of degree n. Tapos ang error, or yung truncation error, kasi ayaw nating mag-work with infinite series, especially when working with computers, kasi hindi kayang computin ni computer yan with infinite number of terms. Puputulin natin siya hanggang n plus 1 terms. So, ibig sabihin, meron tayong degree n polynomial in the variable h, tapos kailangan nating malaman or we need to keep track gaano kalaki yung error. Gaano kalaki yung pinutol natin. Well, Taylor said, kapag pinutol mo siya hanggang sa degree n term, yung error na nakomit mo, which is basically the leftover terms in the summation, will just be h to the power n plus 1 times the n plus 1 derivative of f evaluated at some number c in some neighborhood of x all over n plus 1 factorial. So ito ay kamukhang-kamukha ng error term dun sa interpolation. All right? And I am laying down this foundation because we expect to do this manually, or we expect to have machines do the computations for us. Kaya hindi ko kayang i-feed sa computer yung buong Taylor series expansion. Kasi there would be infinitely many number of terms. Now, I can only afford to feed a finite number of terms in the computer. So maybe I will say, I'll just consider the first n plus 1 terms. So puputulin ko siya, magkakaroon lang ako ng polynomial of degree n consisting of n plus 1 terms. But to keep track, kasi nga hindi lang tayo method-based, kailangan malaman natin gaano kaganda yung error, yung approximate natin. So kailangan natin makita gaano kalaki yung error na nakocommit ko every step of the way. Well, if you're truncating the Taylor series expansion to a Taylor polynomial of degree n, then you are incurring this amount of error. Okay? And this is fine as long as h is a number that is much less than 1. Alright? Kasi kapag kasi h ay mas malaki na kay 1, so h to the power n plus 1 will increase. Alright? So which will make this expansion divergent. Okay? So ang assumption natin dito, h is an infinitesimal number. So the increment between x and x plus h must be small. So assume natin si h ay isang maliit na positive number so that this error will vanish as n increases without bounds. Okay? Kasi yun yung idea. Dapat pag nag-consider ka ng napakaraming terms, dapat yung error ay lumiliit na lumiliit. And that will only happen if h is much less than 1. Actually, when h is less than 1, that would be enough. Okay? So gagamitin natin yung Taylor polynomial of a certain degree to come up with numerical differentiation formulas. So maybe I can illustrate it for today with a simple example. Then we'll extend the process when we start discussing finding more complicated techniques come Friday. Okay. Now, let me see. Okay. So maybe now let's try to derive, say, a 2-point formula of, say, order 1. Okay. Halimbawa, gusto ko tong i-derive. Actually, this formula is derivable. May word ba na derivable? This formula can be derived from the Taylor series expansion. All right. So paano ko siya ma-derive mula sa Taylor series expansion? Well, what I'll do is to take the series expansion of f of x plus h, but I will only consider the linear approximation, right? Kasi nga alam natin ito ay gumamit lang tayo ng 2 points. So you can say it's a linear approximation of the derivative. Kasi 2 points lang yung ginamit mo. Kung meron kang 2 points, nag-interpolate ka, makakakuha ka ng isang linear interpolating polynomial, tapos yun yung dinifferentiate mo. So you can think of it as a linear approximation for f prime. Now, if I'll do the same thing, kunin ko yung Taylor series expansion ni f of x plus h, pero i-truncate ko siya hanggang sa linear term lamang. Right? So, ibig sabihin, kung gusto ko yung Taylor polynomial of degree 1, kukunin ko hanggang may coefficient na h to the power 1. So, what I did is, okay, get f of x. That's what you got here. Okay? So, f of x, tapos, oh, h to the power 1, kasama ka kasi h to the power 1. But I will ignore all of the other terms. So, ito lang yung kukunin kong expansion, but I want to keep track of the error. Sabi yung error ay ito yung itsura, but we are truncating at n equals 1. So, ibig sabihin yung error will be h squared, right? Kasi ang n ko ay 1. Tapos, second derivative evaluated at c all over 2 factorial. So, the order 1, the degree 1 Taylor polynomial is f of x plus h times f prime of x, tapos yung truncation error ay h squared f double prime of c all over 2 factorial mula sa Taylor's theorem. Okay? Tapos remember our goal? Our goal is to find a formula for f prime. Well, I have this. Tapos, uy, may f prime dito. So all we need to do is to compute for f prime in terms of the other variables or the other quantities in this equation. So what I can do is I'll just transpose f of x plus the error term to the left side, then flip the equation. So I'll have h times f prime equals this guy. And then finally, I will divide both sides by h to get f prime. So this is f of x plus h minus f of x all over h plus h f double prime of c all over 2. Oh, I think I committed a typo here. Dapat pala ito ay minus. Tama na. Dapat siya ay minus h f double prime of c all over 2. Kasi dinivide ko lang both sides nitong equation na to by h. Okay. Now, if we will let x sub 0 to be our x, and then x1 to be x plus h, then this guy will be f prime of x sub 0 equals f of x1 minus f of x sub 0 all over, well, what is h? H will be just the difference between x1 and x sub 0, right? X1 minus x sub 0 will be x plus h minus x. That's going to be h. That's the h in the denominator. And then h is x1 minus x sub 0. Pero may negative sa unahan, so magiging x sub 0 minus x sub 1. Tapos f double prime of c all over 2. And we'll get the exact formula that we get by differentiating the Taylor the Lagrange interpolating polynomial. All right. So basically, we have derived this basic differentiation formula in two ways. We use the Lagrange interpolating polynomial on one hand, and on the other, we use Taylor's theorem, okay, to come up with this formula. Well, this formula here is called a two-point formula for f prime. It's called the two-point formula. So, sulat ko lang. Ito ay two-point formula. Kasi gumamit ka ng dalawang points para ma-evaluate yung, o para magkaroon ng estimate para kay f prime. Ano yung dalawang mong points na ginamit? Ginamit mo yung function value kay x plus h, tas ginamit mo rin yung function value kay x. So, it's a two-point formula. And it is said to be of order 1. The order 1 comes from the order of the error. Okay? Kasi pwede nating isulat ito, okay, in big O notation. So si f prime of x na compute natin ay f of x plus h minus f of x all over h, all right, plus some error term, all right? But one thing is, we don't know what the value of f double prime of c all over 2 is. Kasi hindi natin alam eksakto anong itsura ni c. So we cannot compute f double prime of c. And there's actually another problem. It's just that we just don't know c. We don't know what f double prime is. Kasi hindi nga natin alam si f prime, so it is highly unlikely that we know what f double prime is. So we don't know f double prime, we don't know c, so there could be no chance that we can compute f double prime of c. But one thing is for sure, f double prime of c is a constant. So, ibig sabihin yung f double prime of c all over 2 ay isang constant. And remember, how can we get rid of unknown constants? We can use the big O notations, right? So hopefully you remember from AMAT 152 what is the big O notation. Tanggalin nyo lang yung constant, so you'll have a big O of the only thing that matters in the error term will be h. Okay? So si h lang yung magma-matter dito. So the error is of order 1. Kasi ang ang error natin ay big O ni h to the power 1. Okay. Anong interpretation ng big O to the big O of h? Ibig sabihin the error vanishes as fast as how h approaches 0. Okay. So yung error dito sa approximation na to ay paliit ng paliit. Gaano kabilis yung pagliit ng error with respect sa pagliit ni h, magsing bilis yung pagliit ng error sa pagpunta ni h kay 0. Okay? If we want to make the error small, we make h small or the increment very small, as what we have concluded before. But how fast will that be? Magkasing bilis si h at saka yung error mag-approach ng 0. Okay? And that's why it is called a formula of order 1. Kasi ito ay big O ni h to the power 1. Okay? And another characterization here, it is a forward formula. Because we're using x and then we go one step forward, papunta kay x plus h. Kaya ito ay isang 2-point forward formula of order 1. Now, in the next few sessions, we will discuss how to derive a, say, a 3-point backward formula of order 4 or a 5-point centered formula of order 2. So yun yung titingnan natin. And in the next exercise, that's what I want you to do. All right? Ang papagawa ko sa susunod na exercise, magbibigay ako ilang points yung gagamitin. Forward ba? Backward ba? Or centered formula ba? Tapos sasabihin ko kung ano yung order. But we'll recall all of this next time before I start deriving some other formulas and illustrating to you how the process will work. But essentially, that's our plan. That's our game plan to find arbitrary differentiation formulas. So actually, in this chapter or in this module, you will learn how to create your own differentiation formula. So pwede kang gumawa ng 3-point Egargin formula for the derivative. Ano? So you can make up your constants, make up your own formula. Pwede tayong magkakaiba ng formula. Sasabihin ko lang ilang points yung gagamitin, ano yung direction, forward, backward, or centered, tapos kung ano yung order. Then you will see that you will have some degrees of freedom. Pwede kang magbigay. Ano yung coefficient na gusto ko? Halimbawa, 17, my favorite number. I'll use that. So I'll come up with my unique differentiation formula. But it will follow a certain order. Malalaman natin gaano kabilis mag-zero yung error. But that would be for next meeting and something to look forward to para sa lab exercise on Monday. Okay? So let's call it a day here. Let's stop. Do you guys have any burning questions you want to ask right now? While you're thinking about that, just a reminder, meron tayong problem set. I already graded some of the PS 1.1, so kindly look at my feedback there. Ayoko muna mag-comment kasi may mga magsasubmit pa, so ayokong madehado yung mga na-checkan ko na, no? But generally, you guys gave those, I graded, gave very good answers. Parang parang walang bumaba ng ng 9 wala yatang bumaba ng 9.2 so far dun sa mga na-checkan ko out of 10. So, good job guys for those I already graded. Saka na lang yung comments para hindi kayo madehado. Probably next meeting when everybody submitted their problem sets na. Okay. Okay, so any questions before we call it a day? All right, there seems to be no questions. So I hope you guys enjoyed the rest of the day. Thank you for coming and joining me early this morning. And then I hope to see you guys again on Friday. Bye, everyone.
Thank you, sir.
All right, you're welcome.